we looked at differentiation of different functions like the ordinary functions, trigonometric functions. We looked at implicit functions and many others, the logarithmic functions. And we also looked at the second derivative, isn't it? Yes? Okay, so now we are going to look at the applications, and we are going to start with rates of change. When we talk of the rates of change, we mean the rate at which physical quantities increase or decrease with time. So in my simple definition there, you have that this is the rate of increase or decrease in the physical quantity with respect to time. So when you talk about it in terms of differentiation, we have the change in the variable, let's say volume, area, length, height, with time. That is, if it is area, the ADT. If it is volume, the VDT. If it is the length, the L, the what? The T. I like that. Are we together? Hello, do you hear me?
Yes.
Okay, that is good.
Yes, teacher.
Okay. Okay, before we start with the examples on how we can find the rates of change of different quantities, I want us to first take a note of these 2 points. One, that if A is, let's say, the surface area of a two-dimensional figure, in terms of the length or in terms of the radius R, assuming we are looking at a rectangle, that is a two-dimensional figure. That is, it has the length and width. All distances are in terms of length, okay? Or if we are talking about the Cipher, whose dimensions are in radius R, then the ADT, what we call the rate of change of the area or the surface area of that figure, is obtained from the chain rule, where we get the ADR, that is the gradient function or the derivative of A with respect to the variable R or the dimension R, times the rate at which that dimension is changing, that R is changing, that is the RDT. For example, if you are looking at a Cipher or a circle, okay? Then point number 2, if it is a volume, the same, we use the chain rule. We shall have the rate at which volume is changing, that is the V dt, as dV dr. If that formula we are going to use is in terms of R, then times the R dt. So that said, it means we are going to have the variable, let's say volume, in terms of one dimension. I'll give you an example. We have, let's say, a cone. Who can give us the formula that we use to find the volume of a cone? Volume of a cone? Let's see this, guys. Sam, please don't mute your audios. Give me the formula we use to find the volume of a cone. Annette, volume of a cone. Unmute and give me the formula. Talemwa. Talemwa. What is the formula that we use to
I
find the
think it
volume?
I think it is 4 over 3 pi r cubed.
4 over 3 pi what? Can you repeat?
4 over 3
Uh-huh.
pi r cubed.
Pi r cubed. Are you sure? Pi r cubed?
Yeah.
No. A cone? Do you know a cone? Hmm? This figure here, if I do it inverted like this, it has the base, let's say that circular base is of a radius r, and then it has the height, which I can call h. You see the dimensions? It is in terms of the radius r and the height h. So if you give me 4 over 3 pi r cubed, you are wrong, because it is in terms of two dimensions, the radius and the height.
Let me try.
Uh-huh.
It is 1 over 3.
1 over 3.
1 over 3. H pi
Pi is not there.
Pi r no h pi r squared.
H pi r squared. Okay, that is correct. This is the formula we use to find or to determine the volume of a cone. So what I was saying is that if you are to find the derivative of this v with respect to the dimension r, it means you have to find a way of taking away this other dimension, that is the h, so that you can get the dv dr. Are we together? Or if the rate of change that they want is that of the height, then we are to find a way of going out with the r, so that we find the dv dh. So it is either way, depending on what they want, you eliminate one variable, either the h or the what? The r. So such quantities which are in terms of 2 or more dimensions, that's what we are going to do. Let's have examples. Example 1. Hope you have the books. You copy these numbers and you write the answers. Example 1, we have that the side of a cube is increasing at a rate of 0.2 meters per second. Now, which physical quantity is changing there? Hello? If I may change the question, which dimension of a cube is changing? When they say side, what do they mean? Hello? All right. When they say that the side of a cube is increasing at that rate, then they mean the length of a tube. So the dimension that we are looking at here is the what? Is the length, and that length is measured in meters. Okay. So what is given here is the dl, the what? dt. That is the 0.2 meters per second. Meters, that is length, per second, that is the time, the rate of change of length with respect to time, that is the dl dt given. Okay, then they are saying find the rate of change of the volume when the length of each side of the cube is 15. at a time when L is 15 meters. I want you to change that. When you look at the answer here, we have it as centimeters cubed. Okay, let's change this to centimeters. Be consistent. Must have the same unit. Change this 0.2 centimeters per second, not in meters, okay? Hey, so they want us to obtain the rate at which the volume is changing at a time when the length is 15 centimeters. What is the dV dt? The rate of change of volume. Are we together? Yes. So assuming this is our cube, let's say this is our cube. A cube is a three-dimensional figure whose sides are all equal. Meaning, if this is L, then this width is also L, and then this height is also L. Those are the properties of a cube. Okay. Now, who can give us the formula for volume? What's the formula for finding the volume of a cube? Formula for finding the volume of a cube? Mokisa. Is it Mokisa? Mase?
Teacher.
Hey, the formula for finding the volume of a cube?
I think it's the length, width, and height.
Then it gives us
Length cubed.
L cubed. Very good. That is L cubed. Okay. Now we have identified the formula that we are going to use to find the volume. But what they want is not the volume. They want the rate at which the volume is changing. Good enough here. This variable, the volume we are looking at, is in in terms of only a single dimension. That is the length. Okay. There's no any other dimension. There's no any other quantity that is changing that will cause the change in the volume. So to get the dV, to get the dV dt from the chain rule, as I've given it to you in the note there, we are going to have it as dV dl times the dl dt. Okay, we get the derivative, okay, of v with respect to L, and then that of L with respect to T. You know how the chain rule works, eh? Like this, the L is going away, we remain with the dV what? dt. So we need to first find the dV dt, then the dl dt is already given, okay? What is the dV dl? Can someone differentiate v with respect to L and give us the answer? This is the formula that we are using to get the dV dl.
3L squared.
3L squared. Very good. You know how to differentiate. We use the basic method. You drop the power, you reduce the power by 1, okay? So we have now the dV dl. We are going to substitute it in our formula here, provided by the chain rule, and we get the dV dt, okay? So dV dt is now equal to, when you substitute this one here, we get 3L squared times dl dt, of which dl dt we have it as 0.2. Very good. So times 0.2. What do you get when you multiply 3 and 0.2?
0.6.
0.6, eh? Okay, so this will give us 0.6 L squared. Okay, so that is our dv dt. Okay, that is 0.6 L what? Q squared. Now we have our formula for finding dv dt. To find that dv dt, when L is 15 centimeters, we just substitute this 15 in our formula for finding the rate at which the volume is changing. Therefore, dv dt is now obtained as 0.6 into the length, that is at L equal to 15 centimeters, okay? That is 15 squared. And then we get our value dv dt. That is the rate at which the volume is changing when the side of the cube is 15 centimeters. So what do you get from your calculators? 15.
135.
What?
135.
135. Seriously?
Yes.
135. Okay.
Sid.
135. So this is going to be in centimeters.
Cubed per second.
Per second. Very good. So I think you're going to ignore this this answer you see here. Ignore it. The one you see in the notes. It is wrong. This one I put it was obtained when the side of the cube is 5, not 15. Okay. So our value we're using here is 15, not a 5. So that's why in the question I have 15 because that answer was obtained using a 5. But here the correct answer is 135 when you use 15 as the length at that time t. Okay. So that is the rate at which the volume is changing with the time. At the time when the length is 15 centimeters. Can we have example 2? Any question about that first example? No? Hello? Okay. If you don't have questions, we continue to second example. There we go. That's the second example. We're looking at now the spherical Barroon, Cipher. The first one was a cube, or they can use a cuboid, okay? A cube or a cuboid. Then in this second example, you have a sphere. So a spherical balloon is inflated at a rate of 3 centimeters cubed per second. Find the rate of increase of the radius when this radius is 15 centimeters. Are you getting that?
2 centimeters.
Yeah?
2 centimeters.
Oh, okay. When this radius is 2 centimeters, okay? All right, we have the 3 centimeters cubed per second. That value stands for what? You have to identify the rate given. When you look at this 3 centimeters cubed per second, what does it mean? Which rate is that?
Change in the volume.
Very good. How do you get to know?
Sir,
Hey. Okay. A quick answer, you can tell from the unit given here. If the unit is in cube, that is volume. Okay. If the power on the unit is a square, then that means area. Okay. And if the power is 1, then that means the length. Is that clear? Length or radius. Okay. Yes. Annette, have you got that?
Yes.
Hey, so you look at the unit given here in the rate. If it is a cube, that is volume. If it is a square, that is area. And the power 1, that means length or radius or height. Okay. So the value given here is the rate, or it stands for the rate of change of volume of this spherical balloon, which is being inflated. Okay. So dV dt is given to us as a 3 centimeter cubed per second. Okay, 3 centimeters cubed per second. That is dV dt. Now, after identifying this one, then you ask yourself, what do they want? In that question, you can tell us, what do they want? They want us to find what? Is Norwega present?
find the rate of increase in the radius.
That is mathematically written as the what? dr dt. Very good. So we are looking for the dr dt. dr dt. I think it looks like a V. Let me try to change it, modify. That is the dr dt that we want at a time when the r is equal to 2 centimeters. Okay, when r is 2 centimeters, you can even write it there like that. When r is 2 centimeters, what is the r dt? Okay, so you look at the figure they are talking about. It is a sphere. Okay, a sphere. Then its dimensions are in terms of the radius. Okay, so we are rating the volume and the radius. Therefore, we have to first quote the formula we use to find the volume of a sphere. What is the formula for finding the volume of the sphere? That's why I said you need to know this formula that we use to find volume and area of these different figures. It is what?
It is 4 out of 3
4 out of 3
pi r cubed.
pi r cubed. Very good. That is correct. So it is in terms of 1 dimension r. That is 4 over 3 pi r cubed. Correct formula. Okay. So after quoting that formula, then you can use it to find the dv dr. Okay. The derivative of v with respect to r, which we can apply in our formula provided by the chain rule to find the dv what? The dv dt. So in our chain rule, we know that if we are to find the dv dt, if we are to find the rate at which the volume is changing, then this is given as dv dr times dr dt. The rate at which the volume is changing is equal to the derivative of v with respect to r times the derivative of r with respect to t. You can see it here in the notes, that note Roman numeral 2. Is that clear?
Yes.
And in this case, we are not looking for dv dt, because dv dt is already given, okay? Dv dt is already given, it is here, okay, as 3 centimeters cubed per second. What we are looking for is the dr dt, this one here. That is what we are looking for. So what we are going to do is just to make this the subject of the formula, okay? Am I clear on that?
Yes.
Okay. Now, we have dv dt, but the question is, do we have dv dr? No, okay?
No.
So we need to first find the v dr, and as we had it in the first example, we get it from the formula we have put up there for finding the volume of that figure, the sphere. Okay. Someone is microphone is giving feedback. Can you first unmute your audio? All right, so we are going to use this formula to find the dvdr. What is dvdr? From that formula, dvdr is equal to is Tarema still in class?
Yes, sir.
What is dvdr?
DVDR is 4 pi r square.
4 pi r squared. Is everyone okay with that?
No.
Okay, someone is not okay with it. We are differentiating this v with respect to r, meaning 4/3 and the pi are constants, okay? We are not looking at them, we are looking at r. So to differentiate this, we just drop the power and reduce the power by 1. So when you drop this power, that 3 will go with this 3. You remain with the 4, okay? Then you reduce the power by 1, you remain with a 2 as the power on r. Is it clear now? Say yes, very fast.
Yes.
Good. So we
Yeah.
can now continue. So this is dv dr, okay? That is dv dr. Now, this is what we are going to substitute here in our formula to get what we want. Therefore, from this formula, we shall have dv dt, which is 3, equal to, we substitute here the dv dr, which is 4 pi r squared. And then we multiply it there, the dr, the what? Dr dt. That is what we have. And from that formula, we can now make dr dt the subject of the formula, and we get dr dt as, we are dividing this one there. So we shall have 3/4 pi r squared. Are we together there? Yes?
Yes.
All right.
Yes.
Yes.
That is good. So that is the final formula we're going to use to find our dr dt. And the dr dt, they want the rate of change of the radius that they want. They want it when, or at a time when r, when r is equal to 2 centimeters. So we are going to substitute this 2 where there is r, and we get the r dt as 3/4 pi into a2 squared. That is the substitution we have. Okay. And what do you get when you feed it in your calculators? Or we can leave it in terms of pies. I think it will give us 4 times 4.